Okay, guys, let's have a look at our givens here to start with. Okay, so a 1.5 kilogram rock, what are they giving? Mass. Okay. All right, is dropped over the edge of a cliff. What did they just tell me? Initial velocity is? Zero, right. Okay, 30 meters above the surface of a lake. What did they give me there? Height, okay? Could be distance too, okay, but we'll write it as height for now. Okay, height initial or final?
Initial.
Probably initial. They're talking about where it was dropped from. That seems like the start of it. Okay, and we're also going to write down that, this could be a distance as well. Okay, we don't know for sure yet. Meters measures distance, so it could be both. What is the speed of the rock just before it strikes the surface? Well, I already know initial speed is 0, so that must be that I'm looking for the final speed. Okay, what would my final height be then? 0. It's just before it hits the lake. That would be a height of 0. All right, so final height, 0 meters. All right. Is there any work being done in this question?
No,
How do I know?
because there's a 0 in initial velocity and a 0 in final height. So there's a 0 on both sides of the equation.
Okay, there is a 0 on both sides of the equation. Doesn't necessarily mean I haven't done any work. Could be a sign that I haven't. What's something that's missing that I would need for work? Force, yeah. Okay, I don't have force here. If there's no force other than gravity, there's no work. Okay, so I know this isn't a work energy theorem question. The other thing looking at this, if I'm holding a rock out over a cliff, what kind of energy does it have? Potential. It doesn't have any kinetic, does it? If I let it go, the potential energy gets turned into kinetic. Would the two be equal? So then it's a conservation of energy question. If EI equals EF, there's no change in energy. There can't be any work being done. Okay, so we're going to say that this is a law of conservation of energy question for a couple of reasons. That's why we walked through. What is it missing? What's happening in this question? These are all thought processes we want to go through when we're determining what kind of question we're dealing with. All right, so this is initial mechanical energy equals final mechanical energy. How do I calculate mechanical energy from yesterday?
Potential energy plus kinetic energy.
Right, okay? So I'm going to expand this out to say my initial potential energy plus my initial kinetic energy equals my final potential energy plus my final kinetic energy. Now, we've already talked the next step through, but let's do it again. Are any of those forms of energy 0 given the context we were told?
Yes.
Okay, which ones?
Kinetic initial.
EK initial, okay, because it said it was dropped. That would mean its initial speed is 0 and it would have no kinetic energy. And which other one?
Potential
Final potential, right, because our final height is 0. All right, so then that simplifies this question down a lot. I'm down to this. The initial potential energy of the rock equals the final kinetic energy of the rock. Okay, everyone follow my reasoning so far? Okay, can I plug formulas in now?
Yes.
Yeah, I have to. I can't simplify any further, so now I have to expand. What's the formula for potential energy?
MGH.
M times G times H, in this case initial. Okay, and what's the formula for kinetic? 1/2 mass times speed squared, and it would be the final speed. All right. So the energy is the same, initial and final. Okay, I'm looking for the final speed. So I need to get VF by itself. What do I do?
Divide what's happening half of m.
Right, divide both sides by half of m, because right now I'm multiplying all three of these things together. The opposite is divide. What happens to m? It cancels. Doesn't energy depend on mass? Like mass is in both of those formulas. Energy depends on mass, does it not? Like we said, if two objects were falling towards you, one was a piano, one was a tennis ball, okay, you'd stand under the tennis ball, okay? Because the piano would have more energy and could hurt you worse, even though they're going the same speed. So mass cancels. Here's why. Mass affects energy. I'm not calculating energy here. I'm calculating the what? The speed. And mass doesn't affect how fast you fall. Everything accelerates at 9.81 meters per second squared. It's okay for mass to cancel here because I'm not looking for energy. If I was looking for the final kinetic energy, I would have to leave mass in there because it's part of joules, kilogram, meters per second squared, or meters squared per second squared. I'd have to have it in there. But I'm looking for speed. Speed isn't affected by mass in this situation, okay? All right, so I'm gonna cancel the m. So what I'm left with here is that this equals Vf squared. I just want Vf, so what do I have to do to both sides? Square root. All right, so what I'm gonna be left with is this. The square root of little g times the initial height divided by 1/2 square rooted equals Vf. Okay, and when I plug in my numbers, that's gonna be 9.81 times 30 divided by 1/2, all square rooted. Okay, so square root of okay, so when that hits the ground, it's going to be moving at 24.26, or hits the water because it's a lake, 24.26 meters per second. So they gave me the mass in the question and I didn't need it. Is that okay? It is. Because sometimes people don't like canceling things off, it just doesn't feel right to them. So the mass, if you put the mass in top and bottom, you'd be fine. You'd get exactly the same answer because it would cancel mathematically even if you enter it. Okay? So it's okay if you don't cancel it, but it's a lot easier to punch into your calculator without it. Okay. All right, everybody okay with that idea? Okay? So in the absence of any forces, energy is conserved. It remains the same, because without any other forces, there can be no what done? Work. There can be no work done. Right? That's what we have to look for when we're trying to tell what kind of question we have. Okay? Now, also in a work question, at least in Science 10, we wouldn't get that much information. Right? They gave us 2 speeds, 2 heights. Okay? We would never get that in a work energy theorem problem. We would either get 2 speeds or 2 heights, but we would never get both. Okay? So little things to watch for to help you decide, because I do find that that is a source sometimes of confusion on the unit exam. People are reading a question and they are like, oh, is this a conservation of energy question or is it a work energy theorem question? I'm really confused because I seem to have the same information. Okay? Things to look for. Force. If it's got force in it, it's definitely work energy theorem. Okay? If it seems like it has a lot of speeds and heights, then it's conservation of energy. Okay? And also, in the context of the question, if it doesn't seem like energy is changing, then it's a conservation of energy question. Okay? In this case, the energy doesn't change because there's no chance for it to change. It's converted, but it doesn't change. Okay? All right. These two are very much like what we just did. Okay? So I'd like you to try those 2 questions there. Okay? Number 11 is basically exactly the same as what we just did. Number 12 is very similar, but asks for a height instead of a speed. Okay? Give you a few minutes on those. Can you guys read that okay, or do you need it bigger? All right, so like I said, the first one is very much like the dropping the rock off the cliff. This time it's dropping a water balloon, okay, from a height of 12 meters. So in that question there, we know it's dropped, okay? So we know that VI is 0 meters per second. We know the mass is 10 kilograms. That is not funny, okay? 10 kilograms. is 10 liters of water. That's 2 gallons. Imagine dropping 2 milk jugs plus a little more on top of somebody. Okay? That's not nice. It's not funny. Okay? You'll hurt them. It's not just getting them wet, you're going to hurt them. It's a lot of energy because it's a lot of mass. Okay? And they're dropping it from an initial height of 12 meters. Okay? Now, calculate the speed just before it hits the ground. So that would be the final speed, and then my final height then would be 0. All right. No forces involved, okay? Only gravity is causing this thing to accelerate. That means all that's going on is potential is being turned into kinetic. All right, so that means that the mechanical energy is conserved in this situation. So mechanical energy initial equals mechanical energy final, okay? And obviously you could shortcut this if you were, looking at it. You might not have to write out all of this stuff. Okay, but that means our kinetic and potential energies added up gives us our mechanicals. Okay, so initial mechanical, final mechanical, and then we know that the initial kinetic is 0 because our initial speed is 0. We know the final potential is 0 because our final height is 0. Okay, and we're looking at m times g times h initial equals 1/2 mv final squared. All right, we're trying to get v final by itself. So same as the last question, divide by 1/2 of m. Okay, the mass is going to cancel, and then I need to square root to get VF. So VF will be the square root of 9.81 times 12 over 1/2. When you plug that in, you should get 15.3 meters per second. Okay, questions on number 1? All right, how many people have done number 2? All right, I'm going to give you a couple more minutes on number 2, okay, just because you're looking for something a little bit different on this one. What I will probably do this week, I'm going to see how we're doing on Thursday with this. If we're good with this, then we'll definitely have a quiz on Friday, okay, on work energy theorem, not this, okay, which means we won't have time for a quiz on this. So what I will do is I will actually photocopy the quizzes just like I would if we were going to have a quiz, give it to you, and put the answers on the board like I did for my physics 20s there. Okay, so you can take that home and have a little extra practice with it, okay, over the weekend. So we'll kind of see where we're at, but I'll definitely be giving you the quizzes on, or the quiz on conservation of energy to take home with you as a study tool, and I'll put the answers on the board. Okay. All right, so question number 2, okay, same idea here. We have the mass of the child, but probably won't need it, okay, and remind me after, I'll tell you a little story about mass in these kind of questions, okay. They're on a trampoline, they jump vertically into the air at an initial speed of 1.6 meters per second. Since we're not told otherwise, what should we assume their initial height is? 0. So this is one of those trampolines that actually has a hole dug in the ground underneath it, if you've ever seen those, okay? Or the ones that are indoors and there's like a hole in the floor underneath it, okay? So you're at ground level when you come off, okay? So we're going to assume then their initial height is 0 meters. All right, calculate how high the child will rise. How fast are you going when you're at your maximum height moving upwards? Right. You have to get that. That's something you have to know in order to solve this question. Right? You have to understand that when you're at your maximum height, that's where you stop before falling back to the ground. Okay. So our VF is 0 meters per second, and we're looking for our final height. Okay. So that can be a little bit tricky. You have to have that understanding of projectiles and acceleration. Okay. There's no forces in here except gravity, so energy is conserved. Okay. Initial mechanical equals final mechanical. Right? Initial potential plus initial kinetic equals final potential plus final kinetic. Okay? Now you might be looking at that and going, Coderre, why do you keep writing all that stuff? Because we haven't done a question where where all 4 of those are in there yet. Okay? I put those all in there because we're going to have some questions where all 4 of them are not 0. Okay? And we have to move other things around. So is it patterned? Just like the work energy theorem questions? All right, initially, we have no potential energy because we start at ground level. And at the end, we have no kinetic because we're at our maximum height where we're not moving. All right, so in this one, we're backwards. 1/2 mvi squared equals mghf. Hey, everyone with me so far? All right, I need hf by itself. What do we do with m and g? Divide them over to the other side. What happens to the m?
Cancels out.
Yep. All right, so I've got 1/2 times 1.6 squared divided by 9.81. Okay, that's all there is to this calculation. Not very exciting. They only end up 0.13 meters above the trampoline. It's a little kid, okay? Like that's as high as they go, right? It's about that far, right? It's not like, you know, you're doing flips or anything. It's just a little kid, okay? All right, questions on that one? Okay, so far in all the questions we've done, mass is canceled, okay? And as long as you're solving for a height or a speed, mass is, well, and irrelevant, right? Because your speed is not dependent on your mass. You accelerated 9.81 meters per second squared regardless of your mass. So as long as you're not being asked to solve for a form of energy like final kinetic or initial potential, okay, where mass would matter, mass won't matter, right? So if you're looking for a speed or you're looking for a height, mass will probably cancel out or not be necessary. Do you have to cancel it out? No. I will always give you the mass on an exam or a quiz question for this reason. Years ago, I had a unit exam in this unit and I forgot to put the mass in the question because I wasn't thinking. I didn't need it, right? It's irrelevant for the question the way I had it. And then I had people coming up to my desk. Mr. Coderre, what's the mass? And the first person I was like, it's 500 kilograms. And they went back to their desk. And a few minutes later, another kid came up. Mr. Coderre, what's the mass? And I couldn't remember the number I told the first person. So I'm like, 300 kilograms. And then I heard I'm like, oh. And then I heard a couple of chuckles because there were people who realized it doesn't matter what number I give you, it's going to come out the same anyway, okay? Because mass is going to cancel it. I could have told them it was 250 million kilograms and they still would have got the same answer, okay? So I had to come up to the front of the class and go, guys, the mass for question 7 is like 500 kilograms. Just make sure everybody puts it down because it didn't matter, okay? But it caused a little stress for a few people who had forgotten that it didn't matter or were just kind of freaked out that it wasn't there, okay? And then that I gave 2 people different numbers, okay? In the end, it wouldn't have mattered, right? So now I always give the mass for that reason because you can use it or not and it doesn't matter. Okay. Okay, in a situation like this, with this pulley, okay, if I'm holding it like this, where is all the energy in that system?
The cords that's connected to the weights.
Well, the cord is going to help transfer the energy. Right now in this position, what's going to drive this system might be a better way to say that.
The balls.
Which one?
The heavier one.
The heavier one. Okay? Like, could this one fall? Yes. But it won't because it's attached to one that is heavier, and that one is the one that's going to fall. Okay? So there's a certain amount of mechanical energy in this system based on the fact that the 2 kilogram mass can fall. And when it falls, it's going to pull on the 1 kilogram mass. So this 2 kilogram mass has, okay, if we go m times g times h, that's 2 times 9.81, and let's just say it's a meter off the ground. Okay, so it'll have 19.62 joules worth of potential energy at 1 meter above the ground. When I let it go, and that 2 kilogram mass falls to the floor, will it have 19.62 joules of energy when it hits the floor?
No.
Why not?
Well, because the 1 kilogram box is gonna take some in order to be pulled up.
Exactly. The 2 kilogram mass is going to do work on the 1 kilogram mass. Does that mean that energy isn't conserved? No, it means energy is conserved. Okay? Not for the individual boxes, but for the system. Okay, remember the system is in the definition, okay, or the kind of first introduction we had to the law of conservation of energy. It said, the energy of an object or system remains the same in the absence of any work. Okay? Is there work going on inside the system? Yes, but it's one part of the system on another part of the system. The total system energy stays the same. Nobody grabbed the 2 kilogram mass and threw it downwards. Okay? If that was the case, then there would be work done. Okay? So sometimes it might look like energy wouldn't be conserved if we're just looking at one part of a system. But anytime we have a system, we have to look at it, at least from an energy perspective, as one thing. Okay? Within that system, energy would be conserved. Okay? All right. We did that one already. We did those two. Okay. Or we did ones like that. All right, the pendulum. Okay. We'll talk about the pendulum. There it is. I was actually using this as a pendulum yesterday for physics. The taxpayers are getting their money's worth. They spent no money on this, but it's good for circular motion and pendulums. Okay? Dual purpose. My hoodie gladly gave its drawstring for your learning purpose. Okay, so in a pendulum, okay, the pendulum just swings back and forth, right? You're getting very sleepy. So, the reason the pendulum swings back and forth is because energy is converted and conserved. Okay? How did this thing get its energy?
You doing work on
Right, I did work. I pulled it away from what we call its equilibrium position, okay, where it would rest. Right? I pulled it away from there and I gave it potential and thus mechanical energy. Okay? When I release it, gravity pulls it down, okay, and it accelerates and it changes that potential into kinetic. And that, if this was a perfect system, this thing would go
Forever.
Exactly. Okay, law of conservation of energy would apply, and it would continually, over time, convert its potential into kinetic. Everybody all right with that? Okay. So, do the same rules that we just went over for dropped rocks apply to this?
Yes.
Yeah. Okay. I would know its height above equilibrium because I would take it to that height. I'd know its mass. Okay, and I'd let it go. Would the mass really even matter?
No.
Not in terms of the speed it reaches, but it would in terms of its.
Acceleration.
Nope.
No.
It's energy. Okay? This thing swinging back and forth is not very scary. Isn't a wrecking ball a pendulum? Okay? They can do a lot of work, agreed?
Yes.
They're not moving any faster than this is. Why? Because of its mass. Okay? Remember, mass affects the energy. It doesn't affect the speed. Okay? They would have the same speed, but one that's heavier would have more energy. All right. So, as long as we understand kind of the principle of the pendulum, sometimes a multiple choice question pops up about a pendulum swinging back and forth. Just so you've seen one, okay? Because not too many clocks still use one. Okay? I remember clocks that have pendulums, but I'm very old. Okay? I also remember tablets being made of stone and carbon commandments.
Actually, I have a question. What was the pendulum used for in like the old timey clocks?
The old-timey clocks used a pendulum in order to keep accurate time. So you would know, like, so when a pendulum swings back and forth, it takes, depending on its length, it takes a certain amount of time to complete one oscillation. So to go from here, out, and back. So if you had a pendulum that was the right length, that period would be 1 second. Okay? Or 2 seconds. You can make it however long you wanted to make it. You configure the gears inside the clock to match the period of the pendulum. Okay? And so as it swung back and forth, you could use that to keep accurate time with the gears inside. Right? Now, how long does it, like, if I don't do anything to this to help it, it doesn't swing for very long, does it? No. So old-timey clocks, okay, had a little key, and you would put it in the hole and you would crank it, and there was a spring inside that you would crank the spring, and the spring would keep adding energy to the pendulum throughout the day to make sure that it kept swinging back and forth and kept time as accurately as possible. It was usually good. You only had to do it twice a day. Like you did it before you went to bed, and you did it again in the morning before you left for work, and it would generally be okay. Yeah, that sort of makes sense. Newer ones, they have a battery in them that has a little motor that keeps the thing. It's like, why? Okay, just because it looks cool, right? The pendulum swinging back and forth. Okay, it was the same with like old watches that you had to wind, okay? All you had was a spring in there that just kept clicking the gears. You guys have probably never seen a watch you had to wind. Okay? There's still some, like fancy expensive watches that are self-winding. Every time you move your arm, okay, you actually wind the watch a little bit, yeah, and that just keeps it, keep an accurate time. Yeah, old technology, but it worked. All right. So these are more understanding, less calculating kind of questions here. Okay. So I would like you guys to answer questions 2. So that's got like an A, B, C, and a D in it. And I would also like you to look at number 3. Okay, yeah, so 2 and 4 are the ones I would like you to have a look at here. Okay, let's just do 2 for now since I can't seem to fit it on. Okay, let's just have you do number 2. Okay, just quick kind of answers here and then we'll talk about them in a minute. So if you kick a football and it follows an arc like that, which of course all projectiles follow, okay, what type of types of energy does the football have the moment it leaves the kicker's foot? And we can see that the football is on the ground at that time. So what kind of energy does it have? Kinetic. Okay, he will have booted it as hard as he could, okay, giving it a whole bunch of speed. There might also be a little bit of elastic potential energy in the ball because usually when you kick the football, you put your foot into it, it changes the shape of the ball a little bit and wants to bounce back because of the air inside. Okay, but I'd say mostly kinetic. Okay, what types of energy does the football have at a point halfway to its highest point? Right, it would have both. It's moving and it's above the ground. What about at its highest point? Did he kick it straight up in the air? No. Does it still have some kinetic? Yeah, it's still moving forwards. It may not be moving up. Okay, remember that in energy is scalar, and kinetic energy uses speed, not velocity. It's still moving, so it's still got some kinetic. Probably the least amount of kinetic that it will have, but it still has some. Okay. At what part of its motion are the kinetic and gravitational potential energy equal? Yeah, probably close to halfway. Because it's moving horizontally a little bit too, it might be skewed a little bit off of that, but yeah, probably close to halfway. Okay. And at what part of its motion is the kinetic energy the least? Well, we already said that. At the top. That's where it would be moving the slowest. Okay. At what part of the motion is gravitational potential energy the least? On the ground, beginning and end, yeah. Okay, would be where it's the least. Okay, so looking at this graph here, this has to do with question number 4. Okay, so if I throw a ball vertically upwards in the air, apparently I get a graph of potential energy versus height that looks like that. Is there anything wrong with that graph?
That is showing the height increase, but the potential energy going down.
Right. Is there anything fundamentally wrong with this graph, like according to the rules of graphing?
Mm-hmm.
What's missing? Numbers. Yeah. Okay. I mean, if I don't see numbers on there, I assume that going to the right along the x-axis means height is increasing. That can't be true because that means at some magical height, the ball suddenly starts to lose potential energy even though it's going higher. That makes no sense whatsoever. Okay? This is why graphs have to have scales. Okay? This would be 0 meters, this would be 0 meters, and here would be the maximum height. We still don't have any numbers in there, but I don't know what that maximum height for that thing was. But the scale would have to go up and then back down, which makes no sense at all on a graph, but that's the way that would have to work. That's why scales are important, otherwise they're misleading.
And as the ball gets to its highest point,
Mhm.
it does slow down. Like the potential energy doesn't just keep increasing at the same rate.
Why not? There's no exponents in there, right? As long as height's going up, the potential energy is going up because the acceleration is also constant, 9.81. Okay? I think you're thinking V is squared in kinetic, so it would work differently there, but it actually doesn't for that. That's what that explains mathematically. We're using kind of an average when we're using that mv squared formula. So okay. I get what you're saying. Okay, even though it's slowing down, that doesn't mean that it isn't changing its energy linearly.
Okay.
Yeah. All right. So below that, they have another graph. It's the one of kinetic energy with exactly the same problem. Okay, it's showing that after a certain height, the ball just gets more kinetic energy for some reason. Okay, it's another one where this should be 0, this should be 0, and this should be the maximum, and then that graph makes more sense. Okay, everyone all right with that? So as we go up, potential energy goes
Down.
up. No, potential energy goes up as we go up, right? Because it's dependent on height. Okay, and then as we go up, kinetic energy goes down because it depends on speed, and speed is going to decrease as we go up. All right. That was my pendulum diagram, but it's terrible. Okay, I want you guys to write this one down. This is a good winter example. Okay, a sledder with a mass of 70 kilograms is at a point 30 meters above the bottom of a hill, according to my terrible diagram, okay, and is moving at 1.5 meters per second. I want you to calculate how far above the bottom of the hill they are when they're moving at 7.5 meters per second. Okay? This is about the second most involved question you could get for conservation of energy. Okay? I'll give you a few minutes on that. Okay, fundamentally, this question is exactly the same as the 10-kilogram water balloon and the rock being dropped off the cliff. Okay? In this case, it's a person sledding down a hill. There aren't any forces that we're told of. We're going to assume this all happens in the ideal world where there's no friction or anything like that. Okay? So, my givens are, I know the initial speed, I know the initial height, okay, and I know the final speed. I'm looking for the final height. All right? Since there are no forces mentioned here, can I still assume that this would be true? That their initial mechanical energy at that spot at the top is the same as their final mechanical energy further down the hill.
Yes.
Yeah, all that's happening is their potential's getting turned into kinetic. But this time, they actually have some kinetic energy at the start. Okay, that doesn't fundamentally change it, it just changes that we can't make a whole bunch of things 0 and have it easy. Okay, so I'm going to say the same thing here, initial potential plus initial kinetic, there's my initial mechanical, equals my final potential plus final kinetic. And as we said, none of those are 0 in this question. It still has some final potential energy because we're being asked to find the final height. So what I'm looking for would be in here. Agreed? Okay, before I put in any formulas and things get crazy, can I isolate that? Okay, how do I get that by itself? Right, subtract the final kinetic energy over to the other side. Now, we worked on some questions like this yesterday with the high jumper and all of that kind of stuff, okay, where we said the mechanical energy, which is what this is, minus the kinetic energy should equal the potential energy. Okay, that's really no different than what we did yesterday. All right, can I expand it out now? Now I can put the formulas in. Okay, so I'm going to have m times g times h initial plus 1/2 mv initial squared, so there's my mechanical, minus the kinetic final, 1/2 mv final squared, equals m times g times h final. All right, can I get h final by itself? I can't. Here's something I can do right now though. I'm looking for a height. Is m in every term in this question? What can I do with it then? I can take it out, okay? As long as I'm not solving for a group, okay, I'm looking for just a single variable, I can take mass out, okay? We also know that mass doesn't affect the speed it's going to reach. It would affect the energy it has, but not the speed it would reach. If you're not comfortable taking out the M, that's okay. I put it in the question, right? But I don't need it. So I'm gonna take it out right now. Less things to punch into my calculator. All right, now I want to get HF by itself. What's the only thing I have to move?
G.
G. How do I move it over?
Divide.
Divide it, yeah. All right, I've got HF isolated. I can plug in my numbers now. So I'm gonna have 9.81 times the initial height, which was 30 meters, plus 1/2 times, I think it was 1.5, right? The initial speed squared, minus 1/2 times the final speed, 7.5 squared, and then divide all of that by 9.81. Okay, so all I've done is just plug the numbers in for all the variables I had in the letter equation. Okay, so that should get me the final height of the sled. Okay, so if I punch all that in, okay, I'm gonna have 9.81 times 30 plus 0.5 times 1.5 squared minus 0.5 times 7.5 squared, and then divide that by 9.81. Okay, they haven't gone very far, have they? They've only dropped vertically a little under 3 meters. It doesn't take long to increase your speed from 1.5 to 7.5 down a frictionless hill. Okay, you've only ever gone down hills that have friction. It's nothing like a frictionless hill, I would have to assume, because no one has ever gone down a frictionless hill. Okay. All right, so our final height there is going to be 27.25 meters. Okay, is there a lot of stuff to move around?
Yeah.
Like, this is by far the longest equation you have probably ever written. Okay, and that's okay. But in the end, does it still follow the pattern?
Mhm.
Yeah. Okay, so depending on what you're comfortable with, like for me, I want to start isolating things before I get to this point, because it starts to get messy then. But if you're comfortable moving stuff around after this, okay, then you go right ahead. Okay, wherever you're comfortable doing the moving, you do the moving. Okay, I just like to do the subtraction and addition before I get a whole bunch of other stuff in. All right, so that is the second craziest you can get. The craziest you could get, you wouldn't be solving for height, you'd be solving for speed. What changes? What's the only thing that's going to change here at the end? You'll have to square root it, because v is squared. Okay, but you'd still have exactly the same stuff here. You'd just be dividing by 1/2 and square rooting instead of dividing by 9.81. Right? The pattern is always the same. All right, I'm going to give you guys a little break here for about 5 minutes, and then we're going to try one where you solve for speed. Okay, so on this roller coaster, we have a roller coaster with a mass of 1,600 kilograms, and it is 50 meters above the ground level. Okay, and moving at 5 meters per second. I want you to calculate how fast it is going here, where its final height is 8 meters above the ground. Okay, same pattern. So if you need to look back at the other question, okay, same pattern, just on this one you're solving for v instead of h. Okay, so the final manipulation will be slightly different, but the pattern all the way to it is the same.
The drop doesn't matter.
The drop does matter because that's where the potential gets converted into the kinetic. This area down here is not where we're calculating. We're just calculating here. Remember, the mechanical energy here is the same as here, everywhere, right?
Yeah.
Yeah, so it doesn't matter what it does before that as long as no work gets done to it.
Can you repeat like all the numbers?
Okay, so we start here at 50 meters above ground level, so that would be my initial height. Okay, we're moving at 5 meters per second, so that would be the initial speed. Okay, mass is 1,600 kilograms, final height is 8 meters. Okay, roller coasters are a very typical conservation of energy question. Roller coasters and sleds on hills. You see a lot of those, like you saw bows and arrows and slingshots in the work energy theory one. Okay, so obviously we know it's a law of conservation of energy question. There aren't any other forces going on, so we know EI equals EF. Okay, that's going to mean initial potential, which we have, plus initial kinetic, which we have, equals final potential, which we have, plus final kinetic, which what we're looking for is part of that. Okay, everyone all right with that? Okay, so what I'm looking for is part of EKF. I want to isolate that before I get a whole bunch of other letters plugged in. So what do I do with EP final? Subtract it over to the other side. All right, so I've got EP initial plus EK initial minus EP final equals EK final. All right, now I can plug in all the formulas. All right, so for potential energy, M times G times H initial plus 1/2 MV initial squared, okay, minus M times G times H final equals 1/2 MV final squared. Okay, question so far? All right, what's in every term? Mass. Can I get rid of it?
Yes.
Do I have to? No. Right? But I'm going to because I don't like doing extra work. Okay? There's no sense in me taking the chance of messing up entering 1600 4 separate times in my calculator because I'm not good at that and I probably would make a mistake somewhere. Okay? All right, so now it's gone. I just have to get VF squared by itself. So what do I do with the 1/2? Divide it over to the other side. Okay, now I've got VF squared. I want V. Square root that whole side. Now V is normal. Now all I have to do is plug in my numbers. Okay, so I'm going to have to write smaller here. Okay, 9.81 times 50 plus 1/2 times 5 squared minus 9.81 times 8 divided by 1/2. All right, now plugging that into your calculator, okay, you can do it in separate steps or all at once. I think I've shown separate steps a whole bunch of times here, okay, but if you wanted to do it in one step, it just involves a bunch of brackets. Okay, so I'd say square root of, and then I would go bracket brackets, 9.81 times 50 plus 0.5 times 5 squared, okay, minus 9.81 times 8, close the brackets, divide by 1/2, close the brackets. All right, so we'll be moving at 29.1 meters per second. Okay, so you can do it all at once like that. I don't, because I usually mess up a bracket somewhere and then I get the wrong answer. Okay, or you can do it one piece at a time. And we said, would I get the same answer if I put the mass in there? Okay, so if I do all of this again, okay, but I put the mass in now instead, so bracket, bracket, and I go 1600 times 9.81 times 50, okay, plus 0.5 times 1600 times 5 squared minus 1600 times 9.81 times 8, close the brackets, divided by 0.5, oh, that I have to bracket. 0.5 times 1600, bracket. Yeah. Same number. Why enter 1600 4 times when you don't have to? Okay. Yeah. Same answer either way. Mass has no effect on how fast you go. All right. How are we feeling about that? That's as tough as they get. You won't get one harder than that. And it's not because it's conceptually any harder than dropping a rock off a cliff. It just has more algebra in it. Okay? But, I mean, you guys, your algebra is just fine. Okay? So, not something you need to worry about. I would say you're probably likely to get something along the lines of one of the last 2 questions on your unit exam. I might be, like, a little bit kind, and maybe instead of having it be 8 meters off the ground, I say it's at ground level at the end. Okay? Which means you wouldn't have any
Subtract.
okay, yes, but you wouldn't have, what would the thing be that you would not have to subtract?
You would not subtract from that.
Right, you wouldn't have any final potential energy, so you wouldn't have to subtract that at the end. Okay, little things like that. It's more a matter of me being able to assess whether you can read this situation and go, I have this kind of energy here, I have this kind of energy here, I don't have this, but I do have this. Okay, that's what I would be testing with a question like that. Okay, if I did it that way. Okay, all right. So. Hopefully everyone remembered to hand in their labs this morning, okay? That was due at 8:30, okay? So hopefully those are in. We will go over those tomorrow, okay? Right at the beginning of class, and then we're gonna work on this. And then on Friday, we will have a quiz on work energy theorem. Monday, unit exam review. Tuesday, I will teach you the last thing in this unit. It's efficiency. I'm very efficient at it, takes less than one period, okay? So we can tie up any loose ends on Tuesday before your test on Wednesday, all right?
No, efficient, but not 100% efficient.
Never 100% efficient, nothing is 100% efficient, not even me, okay? All right, so that'll be the plan here going forward. No more labs in this unit, okay? I'm hoping to get one activity and one lab in the last unit, but it might just be the one activity, okay? So, here's what that means for you in terms of your marks, okay? Your opportunities to change your assignment or class work portion of your mark are now greatly limited, okay? Because you're probably only gonna have one more thing after the work lab that goes in that category this semester. Right? It's unlikely we'll have more than two. Two would be the most. Okay? So that part's coming to an end. Also the quizzes. Okay? You're going to have a quiz this week, but not next week. And I don't know if we'll have time for a quiz in the last unit. So there's not a lot of opportunities to change the quiz part of your mark. Because we're coming up on the end. Here's two places though where you have a huge opportunity to change your mark. You still have 2 unit exams. Okay? You have the physics unit exam. And you have the Unit 4 unit exam, right? So that's around 20% of your mark right there, those 2 exams, okay? So it's a big deal to be ready for both of those. And then, of course, you have your final, which is also worth 20. Boy, 40% of your mark is coming up in the next month, okay? So, yeah, you should probably be doing a little bit of regular review from here on out. I'd say the rest of December should be mostly physics, okay? But once we get back, the last unit is short. You can start your final exam review when we get back, right? And take the opportunity to come in and ask questions, go over a few things with me, okay? Before school, lunch, after school, okay? Just to clarify any understandings, because guys, I don't know how many days we're gonna get to do a final exam review. I don't think it's gonna be more than 2. Okay, I think if we're lucky, we'll get 2. Right, so there won't be a lot of opportunity to review in class. Okay, you have to do it on your own and then come and ask questions of me.
Do you know how many questions the final will be?
Yes, around, well, there will be 50 multiple choice. I always make it 50. And probably between 12 and 15 written. It'll depend how much I can combine into one question. So yeah, it'll be about 1.5 times as long as a unit exam, roughly, which fits because you have a little more than 1.5 times as long to write it. Okay? So yeah, you'll have that okay, coming up. Okay, I think we'll leave it there, guys. We got what, 4 or 5 minutes left, but that's what's coming up going forward. Okay. Just looking at the rest of the semester kind of planned out. That's where I think we sit. Okay? All right. Good job today, guys.